This lecture is part 3 of the lecture on Section 4.2, Math 311, course in linear algebra at Western Illinois University. So before we finish up, I want to go back to something we did at the last video, which was one of my mistakes. So if you have your notes handy, number 6, to prove something which wasn't completely correct, and that's my fault. But on number 6, basically we want to have we have these three matrices, A, B, and C, which are alike except for one in one column. And the ith column of A plus the ith column of B is equal to the ith column of C. And so that's what should be the assumption. And then in that case, then the determinant of A plus B is the determinant of actually, let's try it. We'll get it right. Determinant of C is going to be determinant of A plus B. That's what I meant to say. All right. So we'll just cancel this out. And, okay, now that I've completely confused you totally, let me just say that this is true as long as this is true, and to prove it, we can just expand along the ith column. So if we basically, I think if you take here, if you expand this, since the every minor or every cofactor is being multiplied by something in C plus something in D, we can break it up. Okay, so we won't be using this a lot. Maybe in some other linear algebra courses we will. Okay, but I think I finally got that right. Okay, back to a much more important result, and it shows the determinant is multiplicative. That the determinant of if A and B are both n by n matrices, then the determinant of AB is the determinant of A plus times the determinant of B. We've shown that this is true if A is an elementary matrix, but now we can show that it's true for all n by n matrices. And the reason for that is as follows. We're going to break this into two cases. So the Y. Case 1, A is invertible. All right, so in that case, A can be written as a product of elementary matrices. And then AB will be equal to E1 through EK times B by substitution. And then the determinant of AB is the determinant of E1, EK, B, and by the properties of elementary matrices, that this is going to be the determinant of E1 through EK times the determinant of B, which is the determinant of A times the determinant of B. Okay, so basically we're just using the fact that in this case A is the product of elementary matrices, and the determinant behaves very nicely with elementary matrices. So that's the case when A is invertible. Now case 2, when A is not invertible, that means we already know now that that means the determinant is 0. And then that means we also know that the reduced row echelon form of A has to have a row of zeros. Okay, so if R is the reduced row echelon form of A, this must have a row of zeros. Otherwise, it's the rank is full rank. Its rank is n, and that means A is invertible. And so once again, we can write with the reduced row echelon form is obtained by elementary row operations. So we can there are elementary matrices A1 through E1 through EK times A is equal to R. Where these E's are not going to be the same as E's up here, but because these are separate cases for some elementary matrices. All right, and then we're going to multiply both sides by B on the right. And you can check that because R has a row of zeros, ERB must have a row of zeros. Okay. Once again, what we'll have is that this will, by the, because these are elementary matrices, we have the determinant of E1 through EK times the determinant of AB is equal to the determinant of RB, and which is 0. Because RB has a row of 0, so its determinant 0, and because this can't be 0, so this must be 0, so this means that the determinant of AB equals 0, and which is the same thing as the determinant of A times the determinant of B, because in this case this is 0 as well. So it doesn't really matter what B is. Okay. So that works. All right, so this is going to be very, very helpful to us later on. Incidentally, the fact that the determinant of A plus B is not equal to the determinant of A plus the determinant of B. It's pretty easy to see come up with a counterexample to that. Okay. All right. Then once you prove 10, the next result's actually very easy, which is the determinant of A inverse. If A is invertible, then the determinant of A inverse is 1 over the determinant of A. Reason for that is that A times A inverse is equal to I. And excuse me. Okay. Sorry about that again. So that we take the determinant of both sides. And the determinant of I is just 1. And from the previous result, we can break this up as the determinant of A times the determinant of A inverse. Okay, and then we can divide both sides by the determinant of A, which we can do because A is invertible, and the determinant of A is not 0. Okay, so we get the determinant of A inverse is 1 over the determinant of A. Okay. All right, so that's not too bad. One thing another fact you should understand is that the determinant of A transpose is the same as the determinant of A. As you can see, I've already explained why that is. I've written this down. It's certainly true with 2 by 2 matrices. If we take the transpose of A, B, C, D, we multiply this out. This is still going to be AD minus CB. Okay, they're the same. For a 3 by 3 matrix, we can again, with the key here is we can expand along the trick is just to expand along the first column. Okay. And then we use the fact that we get A minus B times C of these smaller determinants, and then we can use the fact that, well, if we know that this is true for 2 by 2 matrices, then if we interchange these two rows, it doesn't change anything, so we do that, and we get the same determinant of this our original 3 by 3 matrix. Okay, so it's true for 3 by 3 matrices, and then in a similar way, you can do it for 4 by 4 matrices. Again, the trick is just to expand along the first column. Okay, basically, so expanding along the first row. You know, the first column is the first row of A transpose and vice versa. So that's why it works. All right. Okay, the last one has to do with Kramer's rule, and in this case, we're going back to solving systems of linear equations, and this way you can always find. So if A is an invertible matrix, if you want to solve this system, this matrix equation, which of course corresponds to a system of linear equations with n equations and n unknowns, we could, if you don't mind calculating determinants of matrices, you can do it using this thing called Kramer's rule, which says that so if A is an n by n invertible matrix and B is a column vector in Rn, we can find the solution to Ax equals B, is defined by this formula right here. That we take the determinant of A with the ith column replaced by B and divide it by the determinant of A, and that is going to be that will do it. That's going to that gives us what all the components of X. Okay. So let me just give the proof give a real quick proof of this, and then maybe we'll do a U1 example or not. So why is this true? Well, so let's suppose that if X is a solution, and let's take let's look at now let's see, what should we do? If we do this first, let's let xi be the determinant of okay, sorry about this. Take consider the equation A times the identity matrix, where with the ith column replaced with x1 through xn. Okay. Now, what is that going to be? So really, what this is the same thing as well, this is the same thing as AE1, okay, AE2, and so on, and then we have x1 through xn here, and then finally we have AEn. Okay. And remember, this we recall AE1 because E, you know, our discussion of standard basis elements, this is the first row of A. This is or the first column of A. This is the last column of A. And everything here is a column of A except for this one, right? Okay. So what we have is we have A times IN with ith column, the ith column. Replaced with, okay, I'm going to start again here. Okay, bear with me. Okay, so let's suppose that AX equals B. Okay. And recall that AEI is the ith column of A. Okay, so if we take A times E1, E2, and so on, and then somewhere we have X in here, and then everything else is just, we're going back to standard basis vectors. Okay, then this is going to be AE1, AE2, and then AX, and then AEN. But remember, this is equal to B, and this is, and so what this is this is A with the ith column replaced with B. Okay. And this is A, and then this matrix was just the identity with the ith column replaced with X. Okay. Now we take the determinants of both sides. The determinant of this will be the determinant of this matrix times the determinant of this matrix, so this is the determinant of A. And if you compute this out, this is just going to be the determinant. This is just going to be xi. And then this is going to be the determinant of A with the ith column replaced with B. Okay. Why is that? Why is this true? Well, you can just do an example. Let's say you have 1, 0, 0, x1, x2, x3, and 0, 0, 1. If you take the determinant of this and expand, maybe just expand by one of these rows with a lot of zeros, you'll have 1 times this determinant, which is x2, and then everything else is 0. So that's why that works. And then we can just divide by the determinant of A. So this is going to be the determinant of this thing divided by the determinant of A. So, all right. So for example, let's say if we wanted to solve something like 3x plus 2y equals 5 and negative 7x plus 3y equals 1. Let's say in this case A would be 3, 2, negative 7, 3. Okay, and then B would be 5, 1. If we wanted to, then x1 would be this would be 5, 1, 2, 3, divided by the determinant of 3, 2, negative 7, 3, which would be 15 divided by 15 minus 2, that's 13, and this would be 9 minus 9 plus 14, that 9 plus 14, that would be 23, okay? And then x2, you could check that this would be 3, negative 7, 5, 1, divided by the same determinant, which is 23. And this would be, hopefully I could get this, 3 plus 35 is 38, so it would be 38, 23. Okay, so that would be, and you can go back and check and do this by basic algebra 1 to see if these solutions are correct. Hopefully they are. A lot of stuff in this lecture. Thank you for bearing with me, and I'll see you next time.